Today we'll be talking about section 3.1, Introduction to Determinants. So if you'd like to follow along in your textbook, you can do that. And of course, I'll be posting a PDF of this document on Brightspace. So recall before we went to break that we talked about 2x2 matrices in the context of whether a matrix was invertible. And while we were doing that, we saw what a determinant was. So the determinant for a 2x2 matrix was multiplying the on-diagonal entries, so in this case, A times D, and then we're going to subtract from that the product of the off-diagonal entries, so minus B times C, and this was our determinant. And we had said that a matrix is invertible if and only if the determinant was non-zero. So it would be really convenient if we had an analog for this for larger matrices. So if we had some way of calculating a determinant where if the determinant were non-zero, then a matrix would be invertible. And it turns out this is something that we can do. So we're going to spend today talking about how to go about doing that. So let's take a look at this 3x3 matrix, and I've labeled every entry with the variables that we've been talking about. So for instance, if we're looking at the entry A12, this would be the spot in the first row, second column. So rows are the first subscript and columns are the second subscript. And down below, this is our formula for how to find the determinant. So let's break this down piece by piece. So we're going to start with A11. This is the entry in the first row, first column, and we're multiplying that by a determinant of a smaller matrix. We're going one size down. How do we find that smaller matrix? Well, we're going to do that by highlighting the row and the column that A11 itself is in. And then the leftover matrix, this 2x2 matrix that's left, this is the matrix that we're seeing here. So we have a special name for this. This is called the matrix capital A11. And what this matrix is it's just the matrix that we find exactly as we just did, removing the first row and the first column. Those are the entries that are left over. So we then go ahead and do this again for the next entry in the first row. So this A12 is the next entry in our first row. There's a minus sign there. We'll get to that in a couple of minutes. So we're going to do exactly the same thing. We're going to remove all the entries in the row that A12 is in and in the column that A12 is in. And all of the non-highlighted entries are what ends up over here. So this is our matrix A12. This is the matrix A with row 1 and column 2 removed. And finally, we have one more entry in that first row. Let's go ahead and get rid of this highlighting. We have one more entry in that first row, this A13, that shows up here. So now we've hit every entry in that first row, and we're multiplying that by the determinant where we remove the first row and the third column. So the row and column that A13 is in. And this is called capital A sub 13. This is the matrix A with the first row and the third column removed. So let's take a look at what this actually looks like with numbers instead of with variables. Let's go ahead and calculate a determinant for a 3x3 matrix. So this is problem 2 in section 3.1. So we have this 3x3 matrix and we want to find the determinant for it. So we're going to start off just like we did on the previous page with this first 0. Here's this first entry in the matrix, and we go ahead and highlight, we highlight the row and column that 0 is in, and then what goes in this determinant is the numbers that are not highlighted, so minus 3, 0, 3, and 1. And then we go ahead and do the same thing, whoops, just lost a number there. I think that's what the number was. Anyway, we go ahead and move back along, so here's our minus 4. The minus sign was part of the formula, so the 4 is what's coming from here. We go ahead and highlight the row and column that 4 is in, and then what is left here is the numbers that are not highlighted. And we're going to go one more time because we have one more entry in that row and column. Losing that 3. We have one more entry in that row and column, so that's the 1 here. And we're going to go ahead and highlight, the entries in that one's row and column. and this matrix here is going to be the non-highlighted pieces. All right, so if we want to figure out the determinant, then we have 0 times this determinant here. We don't need to know what that is because 0 times anything is 0. Minus 4 times, we know how to find a 2 by 2 determinant. We go ahead and multiply the entries there on the main diagonal and subtract off the entries on the off diagonal. I think I wrote the wrong number here. I think that was supposed to be a 5. Let's rewrite history and pretend like that matrix had a 3 there the whole time. Sorry. And then onto that, we'll add on 1 times the matrix of this 2 by 2, or times the determinant of this 2 by 2 matrix, which here we've got 3 times 3. And then we're going to subtract off minus 6. So altogether, we have minus 4 times 3 plus 1 times 9 plus 6, which is 15. So we have 15 minus 12, which is 3. All right. So now that we kind of see how to make a determinant or how to find a determinant in a 3 by 3 matrix, let's go ahead and formalize this definition. So our definition for a determinant is this. It looks a little bit long, but it's exactly what we've just been doing. So here we have our first entry in our first row multiplied by the determinant of the leftover pieces once we remove that row and column. And then here we subtract off the second entry in the first row times the corresponding determinant, and so on. So what we're actually doing with these minus signs is we're alternating plus, minus, plus, minus, plus, minus. So the first piece is a plus, the next piece is a minus, the next piece will be a plus, the next piece will be a minus, and so on. And that plus, minus, if we write this in summation notation, is represented right here. So that's minus 1 to the 1 plus j. That's how you know what the sign is. So we're finding the determinant by what's called expanding along the first row, right? We're taking an entry in the first row, multiplying it by the determinant, taking the next entry in the first row, multiplying it by a determinant. But it might be useful to expand along other rows or columns instead. So depending on what your entries are in your matrix, different rows or columns might be more useful. And it turns out we can actually do this. So we do this by looking at what's called a cofactor. And a cofactor is literally just that, it's same exact determinant that we found. So the ijth cofactor looks at the determinant of our matrix if we remove row I and column j, and then also multiplied by what the appropriate sign is. So our appropriate sign is minus 1 to the I plus j. And if we have this, we can do what's called cofactor expansion to calculate the determinant along any row or column we want. So suppose we wanted to calculate the cofactor expansion along a row I, then we'd take the first entry in the row I, multiplied by the appropriate cofactor. Add the second entry in row I, multiplied by the appropriate cofactor. And when I say appropriate cofactor, again, all I mean is we're removing row I and whatever column we have, and just taking the determinant of whatever is left over. And then we have a plus or minus 1, depending. We can also do this down any column j, so we'll take the first entry in column j multiplied by its cofactor, plus the second entry in column j multiplied by its cofactor, and so forth. So let's see what this looks like in action. So if we're trying to find the sign for a cofactor, we can literally calculate it out as we just saw, or we can think of the matrix in a checkerboard pattern. So for instance, we have sort of this alternating plus minus across and down. And so if we're trying to find the sign for the cofactor in the second row first column, where that arrow is pointing, that should be a minus 1. And if we actually calculated this out, this would be a minus 1 since we want to do minus 1 to the row number plus the column number. So here the row is 2 and the column is 1. So that'd be minus 1 cubed, which is negative 1. So either way you want to think about it is fine. So let's take a look at another example. This is problem 6 in section 3.1. And we're looking at this, we could expand along the first row like we've been doing before, but we notice that in the second row here, there's a 0. And a 0 is nice because then we have to do less math in figuring out what the determinant is the cofactors that we would multiply 0 by. So let's go ahead and expand along the second row this time. So we start off with the first entry in our second row. And we notice the sign for that from our checkerboard pattern should be a negative. So this should be negative 0. And we don't have to figure out what the determinant is because 0 times anything is 0. But let's actually just write it out anyway for practice. So we can highlight the row that 0 is in and the column that 0 is in. And what goes into that determinant is what is left over, what is not highlighted. Okay, and then to that, oops, there goes a 5. To that, we're going to add on the next entry in our second row. And this time, this should be a plus because that's the sign that it would be in the checkerboard pattern. So we have a plus 3 times the determinant of that matrix, where if we remove the row and column that 3 are in, then we just write down the highlighted entry. So 5, 2, 2, 7. And then let's see if I can do this without, ooh, nice. All right, and then to that we have one more entry in that second row. That entry is a minus 3, and that should be a negative from our checkerboard pattern. So we're subtracting negative 3, and then we go ahead and highlight the row and column that minus 3 are in, and what goes in this determinant is everything that's not highlighted. So 5 minus 2, 2 minus 4. So now we can find the determinant. So we have 0 times something, which is still 0, plus 3 times the determinant for this. We take the on-diagonal entries, so 5 times 7 is 35, and we subtract off the off-diagonal entries. And then we're going to subtract a minus 3, so adding 3 times 5 times minus 4 is negative 20, and subtracting off minus 4. And we go ahead and add that all up, and I believe that makes 144. Okay. Let's look at one more example, and this one's going to be quite a bit bigger. Oops. So here we're going to look at the determinant for a 5 by 5 matrix. And as we're first looking at this looks pretty scary because 5 by 5 is much bigger than what we've been using before. But we'll notice that if we expand along the first column, right here, the first column is all zeros except for one entry. And so if we do this, then all of those cofactors are not going to matter because we're multiplying them by 0 anyway, so they'll go away. So let's try, let me get this zoomed in the right way. Whatever, there we go. Okay, so let's try and find the determinant expanding along that column. So the determinant of A is going to be 1 times taking away the row and column that one belongs to, the determinant of what is left. So 6, 7, 8, 9, 0, 1, 2, 3. I was really creative in coming up with this example for you guys. All right, so 1 times that determinant. So what is this determinant? If we are looking at this determinant, we'll notice that again, this first column is mostly zeros. So we'll go ahead and find, expand along that column. So we're gonna multiply by 6 and then remove the row and column that 6 are in. And we're gonna multiply that by the determinant of the numbers that are left over. So 1, 2, 3, 0, 4, 5, 0, 0, 6. And again, we're done here, right? Because technically we should add 0 times that corresponding cofactor plus 0 times that corresponding cofactor plus 0 times that corresponding cofactor. But all of that just ends up becoming 0. So we can stop here. Okay, so now we're down to a 3 by 3, which is a bit more manageable. And again, we'll notice that this first column is mostly zeros. So let's expand along the first column again. So we have 1 times 6 times 1, which is our first entry in that column. Go ahead and remove the row and column that are there, times the determinant of 4, 5, 0, 6. And now we're to a 2 by 2 determinant, and we know what to do with that. So we'll go ahead and pull down our 1 times 6 times 1, and then we go ahead and multiply the on-diagonal entries and subtract off the off-diagonal entries, but that's just 0. So this gives us 36 times 4. Oh, oops, this one is the one that's 144. I think the other one was 45. I'll change it on the notes. Okay, so you'll notice as we did this, because we had all of these zeros, effectively what we just did is we multiplied every entry that was on the diagonal, because all of the zeros ended up getting rid of everything else. And this can be expanded into any size of matrix. So if A is a triangular matrix, so that means I've only got numbers in a triangle and everything else is zeros. If A is a triangular matrix, then the determinant is the product of the entries on the main diagonal of A. And that's what we just saw with this example. So if you end up seeing a matrix with a lot of zeros and you pick your row or column that you want to expand along cleverly, then it can cut out a lot of the arithmetic. So today we've seen what a determinant is and how to find it. In the next video, we'll talk about some properties of determinants and some other shortcuts for how to find them. So as always, if you have any questions, feel free to email me or sign up for my virtual office hours. And I'm going to start holding drop-in sessions during our class time, the first class of the week. So if you're interested in that, you can come to that as well.